Hello, class. This is a run-through of the equilibrium simulation from Glencoe. Sometimes students have trouble accessing this one because it uses Adobe Flash Player. I'm in Google Chrome. I'm just going to click on there and allow, and as a result of allowing it, the simulation should pop up. If you have trouble accessing this, then you can always Google Adobe Flash, Google Chrome, and there's a list of suggestions for how to enable this. But in the meantime, if you're not able to get it to work, you can follow through this video and treat this as sample data that we can use to answer the questions. So I went to the website, I clicked on the equilibrium simulation. Under reactions, this is step 2 under the directions. It says select H2 and I2 so that we end up with 2 moles of HI. Then my direction is to start the reaction, and I have to pause the video every 1 second and record the information on the table below. You have to manually keep track of your time to do this, and I've already put the first row of data in for us. We can see that the concentration here is 50% for my reactants. I can see it's 50% for my products. I also see down in the bottom left corner, my K value is 2.25, and that is 0.9 over 0.4. 0.9 comes from the forward rate, 0.4 comes from the reverse rate. And then Q is 50 over 50, which is related to the concentrations. Q is equal to 1 at this point in time. So I'm going to go ahead and I'm going to start my reaction. 1 Mississippi. Pause. And then I can evaluate. I see now that I'm at 40.38% and 59.62% of reactants. After 1 second, I see that the concentration of products has started to increase, and I went from 10 particles of each to a mix of 8 on the reactant side and 12 on the product side, which means the forward rate is proceeding faster and the reverse rate is proceeding at a slower rate. I can also see here that my K value remains unchanged because that's related to my forward rate and my reverse rate. But because my concentrations have changed, my Q value has increased to 1.48. So let's go through 1 Mississippi. There's another second. Again, if you're doing this on your own, the data doesn't have to exactly match this, but it's an experiment, right? It's a virtual lab. So as long as you are in the ballpark, we should be okay. 36.1 and 63.9. K is still the same, and I'm up to 1.77 for my Q value. 1 Mississippi again. All right. Record my values. And you'll notice that the Q value is getting closer to the K value as time goes on. So let's see what continues to happen. The other thing you can check on is this graph here for the concentrations. The concentrations for the forward reaction are increasing. And then, actually, I think the colors are a little misleading here. It says that concentration is increasing here. This top line must be our products, even though it's in red. And then the bottom line must be reactants because they are decreasing in concentration. So we can see that reactants are going down, products are going up. You'll notice that the rates are relatively the same at this point in time. So we'll do another 1 Mississippi. All right, 32.31 and 67.69. Oops. We'll just keep going until we reach equilibrium. 1 Mississippi. All right. So you might have noticed at this point in time that when we first started, uh, we look at our data, the Q value increased significantly for each 1 second that passed. And now we're starting to get to a point where the change is not as great for every 1 second that passed. Same thing if you look at the concentration of reactants, we dipped almost 10% after 1 second, but then we dipped about 4%, and then we dipped only about 3%, and then only 1%. So the rate of change is decreasing as we proceed. And now you can also see with our reaction rates, these bars, if you've been paying attention, have been getting closer and closer together. So we'll do another 1 Mississippi. Two 2.18, 1 Mississippi. Mississippi. See, we're getting smaller and smaller change. One thing to notice is that these lines for the concentration over time are starting to flatten out as well. And then these bars look almost equal here, so we'll see. 1 Mississippi. One Mississippi. And it's crude. It's not a perfect measurement or perfect estimate, but that's all you need to do. 1 Mississippi. One Mississippi. And at this point, you'll notice that my Q and my K value is now equal. When Q and K is equal, it looks like the forward and the reverse reactions have also become equal. At least that ratio is. So the ratio of concentration of products to reactants is the same as the forward rate and the reverse rate. And so what we'll probably see over these next couple of data points is that it will stay the same. 1 Mississippi, 30.78, 69.22. That's about the same. 1 Mississippi. And here we go. We start to see this flat line where things are exactly the same because we have reached equilibrium. And 1 Mississippi, good measure. All right. So there are some very subtle, slight changes, but essentially we are at equilibrium. It appears the concentrations have stayed the same. The rate of the forward and reverse reaction are staying the same. And if I let this continue to play, it's just a flat line. So the concentrations are static. There's no longer a net change, but you'll notice that particles are still moving from one side to the other in both directions. They're just moving at equal rates, so the concentration is not going to change at this point in time. So there are some follow-up questions that you can work through now that you have some data. You can also use this video for reference. We also need to briefly talk about part 2. So part 2, if you can't access the simulation, we can do together as well, just so we can have some sample data to answer these questions. So it says repeat the experiment with different starting concentrations. So what I'm going to do is reset the reaction. And it says to change this, use the sliders under initial conditions, that's up here, and then try 3 different sets of initial concentrations. Manually keep track of time with a stopwatch for comparison. So let's say I have fewer particles of A to start and more particles of B to start. So my initial concentration of reactants is 20%. Concentration of products is 80%. I'm going to start the reaction and I'll just count with a stopwatch in a different window. So we'll go start, start. And I see things have started to stop and flatten out, and we're at equilibrium. So this took about 16 seconds in total. All right, and my concentration at equilibrium is 30.77, 69.23, about 16 seconds. Let's reset, try it again. Let's go the opposite direction. Let's start with 80%. I'll go start, start. Now there's probably about a second delay here. All right, so that one's took a little bit longer for the concentrations to stop, about 20, 21 seconds. Let's amend this one because we know it took about a second delay. So we got about 20 seconds here. And something you'll notice here is that at equilibrium, our equilibrium concentrations are still the same, even though we had different initial concentrations of reactants or products. Let's try one more. Let's do something that's a little bit closer. Let's do 8 and 12. There you go. 40%, 60%. Let's see what happens with our rate on this one. Start, start. Okay, so about 17 seconds. So it's interesting. And again, it's not the most accurate of demos, but the key idea here is that the equilibrium concentrations are going to stay the same regardless of what we start with. And then the time that it takes to reach equilibrium may also change. So it looks like here, when we had a higher concentration of reactants, it took us longer to reach equilibrium. When we had fewer reactants, we were able to reach equilibrium a lot faster. For good measure, let me do one more. So what if we start with none of these, no reactants? Start, start. Again, there's about a 1 second delay. And there we go. So about 20 seconds, just for fun. Okay, so we can go ahead and answer the questions there. There are also some graphs that we have to interpret. And then at the end of this,